Hello friends, welcome to my channel Physics Moji. Coming to the next activity, how do you find the focal length of a lens experimentally? Or write the material required to find the focal length of a convex lens and explain the procedure. So now we'll find the rough value of the focal length and the value of focal length by using UV method. So what is U and what is V? We know U is the object distance and V is the image distance. So by using this U and V, we'll find the focal length of the lens. So to determine the focal length of a convex lens, this is the aim of the activity, and apparatus required are V stand, convex lens, meter scale, candle and screen. So coming to the procedure, to get a rough value of the focal length. So to get a rough value of the focal length, we used to follow these steps. First, take a convex lens and place a convex lens on the V stand. Take a V stand and place a convex lens on it. Light a candle and take it far away from the lens. So take a candle and take it far away from the lens. So object is somewhere at infinity. Adjust the screen on the other side of the lens to get clear image of it. So place a screen on the other side of the lens and adjust its position to get the image of the candle on the screen. At certain distance, you will find you can observe the image of the candle on the screen, and to that point, find the distance between this V stand and screen. This will be with the focal length of the lens, because we know that in case of convex lens, when object is at infinity, the image will be at focus. So this will be my focus and this is my optic center, and the distance between optic center and focus is called focal length of the lens. So in this way we can find the rough value of the focal length of the lens. Now let us say UV method. So in this method, place a candle. So as we have taken earlier, we'll place the lens on the V stand and we'll place the object at a distance of 60 centimeters. So object is placed at a distance of 60 centimeter from the lens, and on the other side we'll adjust the screen to form a clear image of the candle. So place a candle at a distance of 60 centimeters from the lens such that the flame of the candle lies along the principal axis of the lens. So adjust the screen to get a clear image and measure the values of object distance and image distance. So after getting the image, find the distance between the V stand and lens. So this will be my image distance, and we have placed the object at a distance of 60 centimeters. This is called object distance, and note down this value in the table given. So in this table we have object distance u1, image distance v1, and repeat the above step for various distances like 50 centimeter, 40, 30, etc. So repeat the same experiment with 50, 40, 30, and note down the corresponding image distances. Calculate the focal length of the lens for each set of values. So for every object distance and image distance, calculate the focal length by using the formula F is equal to UV by U minus V. So you can get a focal length of value of a certain value, and this value will be the focal length of the lens. Coming to the next activity, how do you experimentally find the refractive index of the material of a prism, or write the experimental procedure to find the refractive index of the prism. So our aim is to find refractive index of a prism, and the material required are prism, a piece of white chart, pencil, pins, scale, and a protractor. Procedure: let us take a prism and place it on a white chart. So take a prism and place it on the white chart in such a way that the triangular base of the prism is on the chart. So in such a manner, the triangular base should be on the base on the chart. Let us draw a line around the prism using pencil having vertices P, Q, R. So let the vertices be P, Q, and R. Measure the angle between PQ and PR. So the angle between the lines PQ and PR. So this angle is called angle of the prism, and this gives angle of the prism. Next, let us consider a light AB incident on the light at M and draw a normal at M. So let us assume that on the line PQ at a certain point M, light is incident, and draw a normal here. Let us mark M on PQ and draw perpendicular to PQ at M. Let us mark angle of 30 degree and draw a line AB at M, which gives the incident ray. So here we are drawing the incident ray at an angle of 30 degree. So this 30 degree will be called as the angle of incidence. So this is the angle of incidence. Now fix two pins vertically on the line AB. So place two pins on this line AB. Now let us look for the images of two pins through prism on the other side and fix another two pins, say CD. And now by looking at this, place two pins on the other side on the let the two pins be C and D. Draw a normal to PR and measure the angle between CD and normal, which gives the angle of emergence. So here we have placed two pins AB. So by looking at these two pins, we have placed C and D here. So now draw a perpendicular at this point to PR and find the angle here. So this is our angle of emergence. Measure the angle between the extended two rays, which gives the angle of deviation, and plot the graph between I and D. So now extend the incident ray and extend the emergent ray. So find the angle between these two rays, and this will be angle of deviation. And plot the graph between angle of incidence and angle of deviation. So taking angle of incidence on x-axis and angle of deviation on y-axis. So we can observe that as angle of incidence increases, the deviation decreases initially and reaches a minimum point. From there, the deviation also increases. So this minimum point is called minimum deviation. At minimum deviation, angle of incidence will be equal to angle of emergence. So as angle of incidence changes, the angle of deviation also changes. As angle of incidence increases, angle of deviation decreases and attains minimum value. This we call it as angle of minimum deviation. And further it increases with increasing in angle of incidence. Now tabulate these readings in the following table: angle of incidence, angle of emergence, and angle of deviation. And finally we can derive the formula for finding refractive index of the prism, that is a plus minimum sine of a plus minimum deviation by 2 by sine of a by 2. Coming to the next question, explain the formation of rainbow. The rays of sunlight enter the drop near its top surface. So here we have a water drop, and the the sunrays are entering into the water drop from the top of the surface of the water drop. At first refraction, the white light is dispersed into its spectrum of colors, violet being deviated the most and red the least. So here at first refraction, the light is entering from air to water. So it is entering from rarer medium to denser medium. So here the refraction will takes place. So at this refraction, the white light is splitting into 7 colors, as the violet deviating the most and red deviating the least. Reaching the opposite side of the drop, each color is reflected back into the drop because of total internal reflection. So here on the other side of the drop, it is has been entering from denser to rarer, but we know that the light ray is traveling from denser medium to rarer medium. If angle of incidence is greater than critical angle, then total internal reflection takes place and the light gets reflected into the water drop again. So because of this total internal reflection, the light is getting back into the water drop. Arriving at the surface, at the other surface of the drop, each color is again refracted into air. So here again refraction is taking place. At second refraction, the angle between red and violet rays further increases when compared to angle between those at first refraction. So when compared to the first refraction, at second refraction, the angle between violet and red rays goes on increasing. The angle between the incoming rays and outgoing rays can be anything between 0 degree and 42 degree. So you can observe here the angle between the incoming rays. These are the incoming rays and these are the outgoing rays. So it will be between 0 to maximum angle of 42 degree. You can observe here. So we observe bright rainbow when angle between the incoming and outgoing rays is maximum of 42 degree. So when it is 42 degree, we can see a bright rainbow. You can see the maximum angle here is 42 degree. That is the angle between incoming light and red color. Although each drop disperses a full spectrum of colors, an observer is in a position to see only a single color from any one drop depending on its position. So if violet light from the single drop reaches the eye of an observer, the red light from the same drop can't reach this eye. So it goes elsewhere, possibly downward eye of the observer. See the figure. So if it is from one drop, you can see only one color. So that when it has been taken by the two drops, you can see one color red is deviated, is given out from one drop, and violet is given from the other drop. So when the angle between the incoming light and red color is 40 degree and violet color will be 42 degree. Between the angle 40 degree and 42 degree, we can see all the colors of rainbow. Coming to the next activity, describe an activity to find the least distance of distinct vision. So we know we can see an object at a distance of 25 centimeters clearly and without having any strain. So this distance we call it as least distance of distinct vision. So here we are going to prove this least distance, find the least distance by using an activity. First step, take a textbook and hold it at a certain distance with your hands. Try to read the content on the page. Slowly move the book towards your eye till it is very close to your eyes. You may see that the printed letters on the page appear blurred or you will feel strained. So when you make the book much closer to your eyes, you feel strained. Now move the book backwards to position where you can see clearly without any strain. Now ask your friends to measure the distance between your eye and the textbook and note down its value. Repeat this with other friends note down the distances for distinct vision in each case. Find the average of all these distances of clear vision, and its value will be nearly 25 centimeters from your eyes. So this 25 centimeter distance is called least distance of distant vision, and this value varies from person to person and with the age. Next, activity 2. Describe an activity to find angle of vision, or how do you find the angle of vision. So for this, collect few wooden sticks used in cloth rollers in cloth stores and prepare sticks or pipes of 20 centimeter, 30 centimeter, 35, 40 and 50 centimeter from them. Place a retort stand on a table. Place a retort stand on a table and stand near the table in such a way that your head is beside the vertical stand. So you should stand beside the vertical stand. Adjust the clamp on the horizontal rod and fix it at a distance of 25 centimeters from your eye. So from the horizontal stand, first adjust the stick at a distance of 25 centimeter. Ask one of your friend to fix a 30 centimeter one. So first take a 30 centimeter stick and place to the clamp, which is at a distance of 25 centimeter. Now keeping your vision parallel to the horizontal rod of the stand, try to see the top and bottom of the wooden stick in vertical position. So from this position, try to see top and bottom of the stick at same time. If you are unable to see both the ends of the stick of this distance, adjust the vertical stick on the horizontal rod till you may be able to see the stick at nearest possible distance. So if you are not able to see top and bottom of the stick at once, so if you can see only this part, may try to adjust the distance, so make it to move away from your eyesight. Now fix the clamp vertical stick of vertical shift at the same position without changing the position of the clamp on the horizontal rod. Replace the stick with let it be 40 centimeters because we have taken 30 centimeter here, so at 40 centimeter length. So try to see top and bottom of stick without any change in the position of eye. Repeat the activity with various lengths of the sticks. Here the rays coming from the extreme ends of a object forms angle at the eye. If this angle is below 60 degree or equal to 60 degree, you can see the whole object. But if it is above 60 degree, we can see only part of the object. So the maximum angle at which we are able to see the whole object is called angle of vision. And this value also is value for a healthy human being is 60 degree, and it varies from person to person and with age.